Further, some more problems related to EOQ. First one is EOQ problem with finite rate of replenishment. In this problem, all the assumptions of fundamental EOQ problems are considered except that of instantaneous replenishment. That means here the items will not available once at a time. Instead, they will be available at certain finite rate. So the production process is not instantaneous, or you can say replenishment is not instantaneous. So in this problem, we can divide the total time T into two parts, T1 and T2. At the start of production, Q units are ordered. During interval T, the commodity or item is produced with finite rate K, whereas consumption also goes on with finite rate R, where K is supposed to be sufficiently larger than R. And since production is going with rate K and consumption is going with rate R, so the inventory will build up with rate K minus R. At the end of T1, the production Q units are produced and production is stopped. During time T2, no production is done, only consumption goes on and inventory start decreasing with the rate of consumption which was supposed to be R. Therefore, inventory decreases with rate R, and at the end of T2, inventory becomes 0 and new order is placed. So we can set easily that total time is divided into two parts, T1 and T2. So we can write T is equals to T1 plus T2, and Q units are produced during time T1 with rate R. So we can write Q is equals to K into T1. Similarly, inventories are building up with rate K minus R per unit time. So total inventory during time T will be K minus R into T1. During T2, no items are produced, so T2 is not considered in total inventory. This can be explained with the help of following graph. We have two axes, one is horizontal is for time and vertical axis for inventory. Now QR units are ordered which were starting to be produced with finite rate K. So this distance, that is from axis to top, it will be Q units. Also consumption goes on with finite rate R. So inventory will build up during time T1 with rate K minus R. When all the units are produced, then production stops, and consumption goes on. So inventory decreases with rate R. And at the end of time T2, inventory become 0. Here new order is placed and production again starts with rate K, and inventory starts build up with rate K minus R. This point or this level is the maximum inventory level because after this point production stops. Now total cost will be computed. So for total cost we require two things. One is annual inventory carrying cost, and second one is annual setup cost. So for average inventory carrying cost, the average inventory is required. Total in and it was seen in the fundamental EOQ problem that average inventory was half of the total inventory. So total inventory, that is Q1, is equals to T1 into K minus R. So average inventory will become half T1 into K minus R. And from equation Q is equals to T1 into K minus R, we can put the value of T1. So average inventory will become q upon k into k minus r by 2, which can be or modifiedly written as q by 2 into 1 minus r upon k. So average inventory carrying cost will become the average inventory throughout the year into cost per unit cost of inventory carrying. So FQ will become QC1 upon 2 1 minus R by K. Setup cost will be again in same manner as fundamental EOQ problem is taken as DCS upon Q, and total cost will become average annual inventory carrying cost plus setup cost, that is 1 by 2 QC1 into 1 minus R upon K plus DCS upon Q. Now EOQ is the quantity which minimizes the total cost. So for minimizing the total cost, we differentiate the total cost with respect to Q and put it is equals to 0. That is for minimum del TC upon del Q is equals to 0, which will provide, from here it can be easily seen that if we differentiate it with respect to Q, it will give C1 upon 2 into 1 minus R upon K. And second term will be differentiated, then it will be give minus dcs upon q square. So del tc upon del q is equals to 0 will be equals to c1 by 2 k minus r upon k minus dcs upon q square equals to 0. On solving it with in terms of q, we will obtain that q naught or EOQ is equals to root 2 dcs upon c1 into k upon k minus r. And on double differentiating, that is the second condition of minimization, is second derivative of total cost with respect to q at the solution will be greater than 0. So it can be easily verified that del 2 Tc upon del q square at q is equals to q naught will be equals to 2 dcs upon q cube. Putting q is equals to q naught, we can see that d is a positive quantity, d is quantity cannot be negative, c is the cost which cs is the cost which can also not be negative, q naught is again quantity ordered, so it can also not be negative, so its q will be also positive. So the term del 2 tc upon del q square is positive at q naught is equals to root 2 dcs upon c1 into k upon k minus r. So we can set that economic order quantity is root 2 dcs upon c1 divided by k upon k minus r. Now putting the value of q naught into the total cost, we will obtain that minimum total cost will be equals to root 2 dcs of root 2 dcs c1 upon root 2 dcs c1 into k minus r upon k. Now what will be the optimum number of orders per year? So it was also seen that d is equals to nq. So n naught will be d upon q naught, which will give root 2 dcs root 2 root dc1 upon 2 cs into k minus r upon k. And optimum duration of one production run, or you can say optimum length of time between placing the two successive orders, t naught will be inverse of number of orders per year, that is 1 upon n naught. So it will give t naught equals to root 2 cs k upon dc1 into k minus r. Second EOQ problem is EOQ problem with shortages and instantaneous production. In previous two model, we have said that shortages are not allowed. In next model, now we are taking into consideration the shortages. So we are considering EOQ problem with shortages. Here, all the assumptions of fundamental EOQ problems are considered except the assumption of no shortages. So the assumption of EOQ problem with shortages and instantaneous production will be demand is known and uniform, production of commodity is instantaneous, lead time will be zero, and shortages are allowed. That means in this problem we can divide production run into two parts also, T1 and T2, so that T1 is equals to T1 plus T2, and total quantity ordered, that is Q, can also be divided into two parts, Q1 and Q2. In first order only Q1 quantities are produced, then during time T1 consumption goes on with uniform rate and inventory reaches to zero at the end of T1. During T1 again no order is placed, so the uniform demands creates the shortages or back orders. When shortages reach to a specified level Q, new order is placed and new order will be of size Q, that is Q1 plus Q2. Among these Q units, Q2 units will be used to fulfill the back orders or shortages, and remaining Q1 units will again goes to the inventory. That is, it can be explained with the help of this graph easily. We have two axes, time and inventory. At this point, that is point 0, Q units will be ordered, sorry, Q1 units will be ordered, and production is instantaneous, so upon ordering it will available when order will be placed immediately. Then it start decreasing, and at the end of T1 it will become 0. But since during T2 again only consumption goes on, no production is done, so it will create shortages and go beyond the 0, that is some negative values or below the axis. When it reaches to a particular quantity Q2, then new order is placed and the size of new order will be Q. Then it will available immediately, and in same manner it will go. Now we can easily calculate the total cost, and we can also proceed in same manner as fundamental EOQ problem. The total inventory at a time will be again area of this triangle, that is half Q1 into T1. Similarly, total shortages will be half area of this triangle, that is half of Q2 into T2. Then average inventory throughout the year, that will become Q1 T1 upon 2 divided by the total duration, that is T, that will become Q1 T1 upon 2T. Similarly, annual inventory carrying cost will become Q1 C1 T1 upon 2T. And in same manner, the average shortage cost can be computed as Q2 C2 T2 upon 2T. Average setup cost will be same, DCS upon Q, and total cost will become FQ plus HQ plus GQ, that is annual inventory carrying cost plus annual shortage cost plus annual setup cost. So the total cost will be Q1 C1 upon 2 T1 upon T plus Q2 C2 upon 2 T2 upon T plus DCS upon Q. Now here terms of T1 and T occurs, which should be eliminated from the equation. So for eliminating these terms from the equation, first for T1 and T we consider two triangles AOB and ACD. That is this one. It is AOB, this triangle, and ACD is this triangle. Now in this triangle, these two angles are of 90 degree, that is angle AOB and ACD. Since these are 90 degree, both the angles will be equal, and angles CAD and OAB are same, that can be also written as angle A, that is both angle is common in both the triangle. So third angle will also be equals, that is angle ABO is equals to angle ADC. So we can say that these two triangles, that is triangles AOB and triangle AOB and triangle ACD are similar. And by the property of similar triangles, we can write T1 upon T is equals to Q1 upon Q. Similarly, for shortage, we can easily prove that T2 upon T equals to Q2 upon Q. So putting T1 upon T is equals to Q1 upon Q and T2 upon T is equals to Q2 upon Q, we can obtain the total, we can eliminate the terms of T1 and T from the total cost. Also, here are three quantities we require to obtain for minimizing the total cost Q1, Q2 and Q. We can reduce it by taking into consideration the equation Q is equals to Q1 plus Q2. So in place of Q2, we can put Q minus Q1. So total cost will become half Q1 square C1 upon 2 Q plus, sorry, total cost will become half C1 Q1 square upon Q plus half C2 Q2 Q1 square, sorry, half C2 Q minus Q1 whole square upon Q plus DCS upon Q. Now for minimizing this total cost, we will use the condition that del partial differentiation of total cost with respect to Q1 and partial differentiation of total cost with respect to Q, both the quantity will be equals to 0. Now del Tc upon del Q1 equals to 0 would implies that here we can see a first term will become C1 Q1 upon Q. So 2 and 2 will be cancelled out. On differentiating, it will become C1 Q1 upon Q. Second term will become C2 minus C2 Q minus Q1 upon Q. And partial differentiation of third term will be 0. So that is C1 Q1 upon Q minus C2 Q minus Q1 upon Q equals to 0. Taking LCM as Q, we can easily write it as, and taking Q1 as common, we can write it easily as C1 plus C2 into Q1 minus C2Q is equals to 0, or Q1 equals to C2 upon C1 plus C2Q. We can denote this equation as equation 1. Now second term, that is del Tc upon del Q equals to 0. So it will give minus half C1 Q1 square upon Q square, first term. Second term will be divided into two parts. First is numerator term and second is denominator term. So these two are differentiated separately, or using by differentiation by parts, we can write this as half, sorry, second term will become C2Q minus Q1 upon Q minus half C2Q minus Q1 whole square upon Q square. And third term will become minus DCS upon Q square. That is del TC upon del Q equals to 0 will implies minus C1 Q1 square upon 2Q minus C2 Q minus Q1 whole square upon 2Q square plus C2 Q minus Q1 upon Q minus DCS upon Q square. So we can easily take the LCM as 2Q square. When we take LCM as 2Q square, it will, the equation will become, and also LCM is, in LCM we take minus 2Q square. So equation will become C1 Q1 square plus C2 Q minus Q1 square minus 2 C2 Q minus Q1 plus DCS. And upon opening the braces, we will get C1 Q1 square plus C2 Q square plus C2 Q1 square minus 2C Q1 Q, and in third term will give minus 2C Q C2 Q square plus 2C2 Q1 plus 2DCS. Now from CQ square and CQ square, here is one positive and two negative. So we will remain one C2Q square with negative sign. and C2 Q1 Q1 minus 2 and plus 2 will be cancelled out. So and in first and third term we can take Q1 square common. So it will give C1 plus C2 Q1 square. So we can write C1 plus C2 Q1 square minus C2 Q square plus 2 DCS is equals to 0. Now from equation 1 we can put the value of Q1 in terms of Q. So equation will become C1 plus C2 into C2 square Q square divided by C1 plus C2 whole square minus C2 Q square plus 2DCS. Now from first and second term we can take Q square common, and on solving we get C1 C2 upon C1 plus C2 Q square is equals to 2DCS. So Q naught, that is EOQ, will become root 2 DCS into C1 plus C2 divided by C1 C2. And if we put the value of Q in equation 1, then the optimum inventory level will be obtained as root 2 DCS C2 divided by C1 plus C2 upon C1. Again, the characteristics of this problem: total cost, putting in the formula TC is equals to FQ plus GQ plus HQ, we will obtain that minimum total cost is equals to root 2 DCS C1 C2 upon C1 plus C2. Now second character is optimum level of shortages, that is Q2 naught. So Q2 naught can be easily obtained by using Q is equals to Q1 plus Q2, but due to square root the subtraction is quite difficult. So in same manner we have right here Q1 is equals to C2 upon C1 plus C2 Q. Similarly, if we put the value of Q1 in terms of Q2, then we will obtain Q2 is equals to C1 upon C1 plus C2 into Q. So Q2 will become root 2 DCS C1 upon C2 C1 plus C2. And optimum duration of production, that is T naught, that is one production, optimum length of one production run, that will comes out to be root 2 CS C1 plus C2 upon D C1 C2. The third problem which I require to discuss is EOQ problem with shortages and finite rate of replenishment. In this problem, all the assumptions of previous problem, that is EOQ problem without shortages and finite replenishment are followed, but the assumption of no shortages is not considered. That is, shortages are allowed. You can see can say that we can use all the assumptions of EOQ problem with shortages and instantaneous replenishment except the assumption of instantaneous replenishment. Here we can divide the total duration of one production run into four parts: T11, T12, T21 and T22. During T11, I will explain with this graph. Here we have two axes, time and inventory. Now time is divided into two parts, T1 and T2. Further, T1 can be divided as T11 and T12. T12 during T12, Q1 units, some units are ordered and production will be started with finite rate K, and consumption goes on with finite rate R. So inventory will build up with rate K minus R. After T11, when ordered units, all the ordered units are available, production stops, and during T12 only consumption goes on with finite rate R. So inventory start decreasing and approaches to zero level. And now the second time T2 is divided into two parts, T21 and T22. During T21 only consumption goes on and it creates shortages or back order with finite rate R. When each back orders reaches to a certain specified level Q2, then new order is placed and production starts with finite rate K. Also, the consumption goes on with finite rate R, so back orders are fulfilled with rate K minus R during time T2. Now, since this level will be Q1 and this level will be Q2. But since production goes on with finite rate K, so during time T1, the units produced will be some higher than Q1. Also during T22, the unit produced will be some higher than Q2. That is this quantity. And from this to this, the distance will be taken as Q. That is total produced quantity are Q units. So from it is graph, it is clear that time can be divided. T is equals to T11 plus T12 plus T21 and plus T22. Similarly, Q1 is the total, maximum inventory level. It can be approaches as Q1 is equals to K minus R into T11, or it can also be written as R into T12. Similarly, Q2 can be written as K minus R T22 or R into T21. Now, how we write Q1? Q. So, Q is equals to Q1 plus Q2. Q, but it is can also be written as K into T11 plus K into T22. So K into T11 can be divided into two parts, K minus R into T11 plus R into T11. That is K minus R into T11, that will become Q1, Q1 plus R T11 plus Q2 plus R T22. So Q will become Q1 plus Q2 plus RT11 plus RT22. Now putting the value of T11 and T22 from equation 1 and equation 2, we will obtain that Q is equals to Q1 plus Q2 plus R upon K minus R Q1 plus R upon K minus R Q2. On solving this equation, we will obtain that Q is equals to K upon K minus R Q1 plus Q2. Now again consider T is equals to T11 plus T12 plus T121 plus T22. Now putting the value of T11, T12, T21 and T22 in terms of Q1 and Q2, we will obtain that Q is equals to Q1 upon K minus R plus Q1 upon R plus Q2 upon K minus R plus Q2 upon R. Taking LCM as R into K minus R and solving it, we will obtain that Q is T equals to K upon R into K minus R Q1 plus Q2. From equation 3, that Q is equals to K upon K minus R Q1 plus Q2, we can put the value of Q. So T will be obtained as Q upon R. Now again we calculate the average inventory carrying cost, average shortages cost and setup cost. Average inventory carrying cost will become Q1 upon 2 into T11 plus T12 divided by complete duration, that is T. So putting the value of T11 and T12 in terms of Q1, we will obtain that average inventory will be Q1 square upon 2Q into K upon K minus R. And annual inventory carrying cost will become Q1 square C1 upon 2Q into K upon K minus R. Similarly, average shortage cost will be Q2 square C2 upon 2Q K upon K minus R. Now we put the value of Q2 in terms of Q and Q1 in from equation 3. So average shortage cost will become KC2 upon 2K minus RQ into K minus R upon KQ minus Q1 whole square. And setup cost will become, here instead of DCS upon Q, I have taken RCS upon Q to make the calculation easy. So setup cost is RCS upon Q. Total cost will be annual inventory carrying cost plus annual shortage cost plus setup cost, which will give total cost is equals to Q1 square C1 upon 2Q K upon K minus R plus K C2 upon 2 K minus RQ into K minus R upon K Q minus Q1 whole square plus RCS. For minimum, del Tc upon del Q equals to 0 and del Tc upon del Q1 is equals to 0. Del Tc upon del Q1 is 0 will give this equation, and on solving it we will obtain that Q1 equals to K minus R Q upon K C1 C2 upon C1 plus C2, and del Tc upon del Q will give this equation. In this equation we put the value of Q1 in terms of Q and solve it. Then it will give the EOQ as Q naught is equals to root 2 CS C1 plus C2 upon C1 C2 into KR upon K minus R. And putting this value in the equation 5, that is this equation, the optimum value of q naught q1 naught will be obtained as 2 cs c2 upon c1 into c1 plus c2 into r k minus r upon k.